The nearest star to our Sun is so close in cosmic terms that astronomers casually refer to it as a neighbor. Proxima Centauri, just 4.24 light-years away. That's the kind of number that gets thrown around in documentaries like it means something manageable, like it's a long drive, not an incomprehensible void. But here's what that number actually means in human terms. Light itself, the fastest thing that exists, the thing that crosses a football field in a single nanosecond, takes 4 years and 3 months to make that trip. Not a probe, not a spacecraft. Light. And we can't come close to matching it. Interstellar travel is one of those concepts that lives comfortably in the space between science and fiction. We've seen it in films, read it in novels, heard it discussed at conferences by serious people with serious credentials. And the dream has a logic to it. We left Africa, we crossed oceans, we reached the moon. The narrative of human expansion feels almost inevitable, like the stars are simply the next line on a very long timeline. But that narrative has been quietly ignoring some of the most brutal constraints in all of physics. The gap between sending a probe to Mars and sending anything to another star isn't a gap in ambition or funding. It's a gap between the possible and the physically permitted. We dream of interstellar civilization for good reason. The universe is enormous and we are curious by nature. Scientists have confirmed thousands of exoplanets, some of them sitting in the habitable zones of their stars, some of them rocky, some of them the right size, some of them tantalizingly Earth-like. The Kepler telescope alone identified over 2,600 confirmed planets beyond our solar system. Popular culture has built entire mythologies around reaching them, and the billionaires and agencies of our era speak openly about becoming a multi-planetary species. He does feel like an extension of that ambition. They feel like a destination. What we rarely confront is the mathematics standing between us and that destination. Start with distance, because nothing prepares you for what these numbers actually mean. The Voyager 1 probe is the most distant human-made object ever launched. We sent it into space in 1977, and it has been traveling continuously ever since, using gravitational assists, optimizing every variable we could manage. It is currently about 23 billion kilometers from Earth. That sounds like an extraordinary distance, and in solar system terms it is. But Proxima Centauri is roughly 170 times farther away than Voyager 1 has traveled in nearly 50 years. At Voyager's current speed, reaching our nearest stellar neighbor would take approximately 73,000 years. To put that in perspective, 73,000 years ago, anatomically modern humans were still sharing the planet with Neanderthals. Agriculture hadn't been invented, writing didn't exist. Every civilization you've ever studied, every empire, every language, every war, every scientific revolution, all of it fits inside a fraction of the time it would take our fastest long-distance probe to reach the closest star. But someone will immediately say, we just need to go faster. And this is where the second wall appears, the one built from energy and engineering. Chemical rockets, which still power almost every mission we've ever launched, are operating near their theoretical ceiling. The physics of combustion only releases so much energy per kilogram of fuel, and it isn't remotely close to what interstellar travel demands. Ion drives are more efficient but produce thrust measured in millinewtons, barely enough to accelerate a small spacecraft to meaningful speeds over years and decades. Nuclear propulsion concepts have existed since the 1950s and could theoretically reach perhaps 0.1% of the speed of light. At that velocity, the trip to Proxima Centauri still takes over 4,000 years. The more visionary proposals start to sound like physics fiction rather than science fiction. Antimatter drives, on paper, offer the best mass-to-energy ratio of any known reaction. But producing 1 gram of antimatter using current technology would require more energy than the entire world generates in a year and cost in the range of $60 trillion. We have produced, in total, across all particle accelerators on Earth, less than 20 nanograms of antimatter, ever. The Bussard-Ramjet concept, which proposed collecting hydrogen from interstellar space and using it as fuel, ran into the problem that interstellar space doesn't have enough hydrogen, and the drag from trying to collect it would cancel any thrust the engine produced. Laser sail concepts like breakthrough starshot are genuinely interesting and could theoretically reach 20% of the speed of light using ground-based lasers the size of a country. But they would only work for gram-scale payloads, no crew, no life support, no return trip. And even if none of those engineering problems existed, even if some future civilization cracked fusion propulsion and could, it'd accelerate a crewed vessel to 10% of the speed of light, the journey to Proxima Centauri would still take over 40 years, which means we now have to discuss the human body and what 40 years in deep space actually does to it. This is where the conversation stops being about rockets and starts being about biology, and the biology is unforgiving. Outside Earth's magnetosphere, the radiation environment changes completely. Galactic cosmic rays are high-energy particles that travel at near-light speed and pass through spacecraft walls like they aren't there. Current shielding technology reduces exposure but cannot eliminate it. On a multi-decade interstellar mission, the cumulative radiation dose would far exceed what any astronaut has ever received. These aren't surface-level effects. Cosmic rays break chemical bonds inside cells, including the bonds in DNA. They cause strand breaks, mutations, and cellular death. The brain is particularly vulnerable. Studies of astronauts returning from long-duration missions show measurable damage to white matter, reduced cognitive processing speed, and structural changes in neural tissue. On a 40-year voyage, this isn't a manageable side effect, it's progressive, compounding neurological deterioration. Meanwhile, the skeleton is quietly falling apart. In microgravity, bones lose mass at roughly 1 to 2% per month in the most affected regions. 6 months on the International Space Station produces bone density losses comparable to early-stage osteoporosis in an otherwise healthy adult. Exercise protocols slow this down, but do not stop it. Over a 40-year mission, even with the most aggressive countermeasures we know of, bone loss would reach catastrophic levels long before arrival. Muscles follow the same trajectory. The heart, which is a muscle, shrinks and weakens in microgravity because it doesn't need to work as hard to circulate blood against the pull of gravity. Astronauts returning from 6-month missions sometimes cannot stand unaided for hours. Their cardiovascular systems need days to relearn how to function under gravity. After 4 decades of weightlessness, reintroduction to any gravitational field would likely be unsurvivable. The eyes deteriorate too, in ways that researchers only began to fully understand in the last decade. Fluid shifts toward the head in microgravity, increasing intracranial pressure and pressing against the backs of the eyeballs. The optic nerve swells. The eyeball itself changes shape. A significant percentage of astronauts return from long missions with permanent vision changes. Some require new prescriptions. Some have structural damage that doesn't reverse. On an interstellar timescale, the visual system wouldn't just degrade, it would fail. And these systems don't fail independently. They fail together, each one accelerating the collapse of the others. A compromised immune system struggles to repair radiation-damaged tissue. Weakened cardiovascular function reduces the oxygen available to muscles already fighting atrophy. Cognitive damage makes it harder to manage the physical symptoms, harder to troubleshoot life. Support systems, harder to make the thousands of small decisions that keep a spacecraft operational. The life support system itself is a cascading risk. Every component that fails requires a spare part. Every spare part adds mass. Every additional mass requires more fuel, and the further from Earth, the more a single failure becomes irreversible. A communication signal from Proxima Centauri takes 4 years to reach us. Any distress call would be received 4 years after it was sent, and any response would arrive 4 years after that. The crew is, in every meaningful sense, beyond help. With current technology and known physics, interstellar travel carrying human beings isn't an engineering problem awaiting a breakthrough. It's a confrontation with hard constraints that span thermodynamics, biology, and the speed of light simultaneously. The energy requirements exceed anything our civilization currently produces. The biological damage accumulates beyond any recovery threshold. The distances are so extreme that even radical propulsion improvements don't change the fundamental calculus by enough to matter. This isn't pessimism, it's arithmetic. What makes this genuinely astonishing isn't the impossibility, it's the fact that we know it. We are a species that evolved on a small rocky planet, developed language and mathematics over a few thousand years, and built instruments sensitive enough to detect the atmospheric composition of planets orbiting other stars. We have measured the cosmic microwave background radiation, the echo of the universe's first light. We have mapped the large-scale structure of the cosmos across billions of light years. We cannot go there, not with our bodies, not with our machines, not in any time frame that a human civilization could survive long enough to see completed. But we can see it. We can describe it. We can understand what it is made of and how it behaves from a small planet with mathematics and light. That might be the most remarkable thing in the known universe. Not the stars themselves, but the fact that something on one of their planets figured out what they were.